first talk of the day is a vision talk by Professor Nikhil Ranjan Pal, Indian Statistical Institute, Kolkata, entitled Fuzzy Rule-Based Systems, Applications, Design Issues, Solutions, and Open Problems. Where do we stand? The session will be chaired by Professor Satish Kumar, the Halbag Educational Institute. I request Professor Kumar to please come and introduce the speaker. Thank you.
Professor Nikhil Pal is professor in the Electronics and Communication Sciences Unit of the Indian Statistical Institute, and at present is visiting the National Chiao Tung University, Taiwan as chair professor. He received the BSc Physics and MBM Operations Research degrees from the University of Calcutta and obtained MTech and PhD degrees in Computer Science from the Indian Statistical Institute, Calcutta. He has co-authored a book, Fuzzy Models and Algorithms for Pattern Recognition and Image Processing, and edited several books. His current research interests include image processing, pattern recognition, fuzzy set theory, neural networks, evolutionary computation, and bioinformatics. He serves on the editorial boards of several journals, including the International Journal of Approximate Reasoning, International Journal of Hybrid Intelligent Systems, International Journal of Neural Systems, Fuzzy Sets and Systems, and IEEE Transactions on Systems, Man, and Cybernetics. Part B. He is editor-in-chief of the IEEE Transactions on Fuzzy Systems. He has been president of the Asia-Pacific Neural Net Assembly and has served as general chair, program chair, co-program chairs of many international conferences in neural networks and fuzzy systems. He is fellow of the IEEE USA and of the Indian National Academy of Engineering, and I consider it a privilege to chair his session. Professor Nikhil Pal.
Thank you, Satish, for these nice words. You have used a couple of strong adjectives, and I hope the talk justifies that. I'm really thankful to the organizer, particularly to Satish, for inviting me to talk to this really distinguished audience. It's really an honor for me. I wanted to be here for quite some time to this place, Doyalbagh, where Satish is a very good friend of mine for several years, but I couldn't make it. So even from that point of view, I'm very happy to be here. Since I know that this is going to be a very distinguished audience and experts from all kinds of fields, so mostly this would be at the concept level. And there is well, story is not the right word, the motivation for this kind of talk, because I have encountered many situations, both in conferences and outside the conference also, where practitioners have some problems to solve, and I find that the neural network is the tool of choice to solve the problem. In a couple of occasions, I have asked them questions that, why did you use neural network? Why didn't you try other tools like fuzzy systems and things like that? I got some answers, sometimes satisfactory, sometimes not. So then I tried to find out what is the reason why people don't want to use. Well, when I say people, I mean that includes some of the people who really work in fuzzy sets also. Fuzzy systems in many practical applications, although it has many applications already. And so I'll share those things, and in that process I found some of the difficulties and problems which are yet to be addressed. So I'll mention about those things. And for two of the problems, I'll try to give some kind of quote-unquote approximate solutions. Fuzzy sets, we all know that it models two facets of uncertainty. One is non-specificity, this lack of specification, and other is vagueness or ambiguity. But I must mention at this point that almost all applications that we have today that really exploits the fuzziness or ambiguity aspect of it, very few really talk about the non-specificity. And for some applications, that is very important though. It's a tool for modeling uncertainty, which means modeling real life situations, and as well as also this is a tool for problem solving. It's kind of, we can model uncertainty as well as we can solve problems using it. And to me, the most attractive features of fuzzy systems are, it's kind of, if you design a rule-based system, it's understandable, it's readable by human beings. It's not a black box, and that is very important from my point of view. But often again, when we talk about applications, we forget about these and we pay more attention on the numerical accuracy of the system. And there are many applications, starting from unmanned car parking, washing machines, air conditioners, subway control, aircraft, and many places. For many such problems, precise mathematical formulation is difficult. For some of them, approximate solutions are good enough. Like when you're trying to park a car, parallel parking, you really don't care about precision there. Approximate solutions would be good enough. Typically, the number of variables involved, they are not many. And you can always have an expert, or in most cases, you can find an expert who would be able to give you some kind of rules. When I say some kind of rules, it's rules like, I'm sure that all of us have tried to balance a pole on the fingertip. And essentially what we do is we look at the pole, and if the angle is, say on this side, if I call it positive, if the angle is very big positive and also is falling very fast, then we apply force in this direction first. So I'm talking about rules of this kind, and almost everyone can write down these kind of rules because we can use them and balance it. So for this kind of systems, fuzzy logic has been applied, and they are really very good for such applications. And of course, if experts give the solutions, naturally it is readable or understandable. But there are other families of problems where precise solutions are needed, at least we care about, like medical diagnosis. We want to know whether it's some particular type of cancer or not. We don't want approximate solutions to this problem. The application could be such that too many variables are involved. Now again, I must try to clarify, when I say too many, I'm not referring to really few thousands, maybe say 20, 30, 50, where it's difficult for a human being to write down rules. You may not have experts for this kind of problem, and there are areas where you have experts who can make a decisions, but if you ask the expert what rules have been used, what reasons, what he or she has in his mind, it's very difficult to get a clear answer to this problem. And I myself made couple of experiments, like I used to keep my bicycle in a railway station, and that gentleman used to maintain about 500 cycles, of which about 300 are having the same brand as mine, Avon, having black color, almost with same configuration. I used to go and ask him for my cycle. He said, you go there and pick up. Sometimes it would be difficult for me to find the cycle from that small, say from a set of 10 cycles. And then I asked him that, how do you find my cycle? What attribute of my cycle do you use? He couldn't answer. Then I repeated the experiment after 2-3 months. Again, he couldn't answer. So they can solve the problem. So getting the rules from the expert is often difficult. So what do we do for such problems? Fuzzy logic is applied to such problems also. And here what we need to do is, only solution we can have is if we have data, we can use them. For example, we ask the expert about the decision, and then we have some kind of input-output data, and I try to extract the fuzzy system from there. Now this, once we try to do, this raises many issues, and of course there are many methods have been proposed for this. And my talk will be primarily focused on such applications and issues, more specifically to non-control applications, or maybe we can say pattern recognition, function approximation type applications. Although control is still probably the most important area from fuzzy systems point of view, because I get probably 30% of the submissions to the transaction from control area. This talk is going to involve 3 types of models. First one is the Mamdani-Aselian type model, where the antecedents, like if x1 is low, x2 is medium, x3 is high, then y, that is the output, is again a fuzzy sets like big, small, medium. We call this Mamdani-Aselian type model. And then the second one is going to be the Takagi-Sugeno, also called Takagi-Sugeno-Kang model, where the antecedent does not change, but the consequent is a function of the input variable. And third one is a classifier model. For the classifier, there could be other models also. I'm going to use the most simple one, where again the antecedent parts remain the same, but the consequent is just a class symbol, although I write class K, but K is just a symbol like class 1, the class cow, the class dog, and things like that. So these three types of model will be involved. I'm not going to talk about the type 2 fuzzy systems where the uncertainty associated with the membership functions are also taken into account. Now, I want to say a word of caution to protect myself that my purpose is not try to sell fuzzy logic in 2007, nor I will try to, nobody should think that I'm trying to underestimate neural networks or any other tools. I am going to use neural network just for contrast for some selected applications. The word selected is very important here, because my living, I just want to emphasize, comes equally from both fuzzy systems and neural network, and also evolutionary computing. And there are problems like prediction of protein folds, where mostly people talk about 100 dimension, 1000 dimension, and really you cannot apply a fuzzy system. So I know all those things, so please don't misunderstand me. Fuzzy systems is not an all-cure solutions. The whole idea is there are areas where it can do a good job, but there are some problems to use it also. This fuzzy logic and neural networks, they're two important ingredients of computational intelligence, but Satish here calls, I think, soft computing, which I do not like the term, so I prefer to call computational intelligence. But it started with the term soft computing. Both of them have universal approximation capability, neural network and fuzzy systems. Both of them have been extensively used in pattern recognition and function approximation type problems. Well, if you ask me about the black box characteristics, the neural network is a more stronger candidate. It's really difficult to interpret, although someone may say that, okay, we can try to extract rules from a neural network, but to me it's not really something very natural. Fuzzy systems from that point of view is more readable. Designing from data, again, both fuzzy systems and neural network both have been used, both can be designed from data. Level of difficulty associated to design from data. Now here, neural network will see it's easy, it's not very difficult. Well, fuzzy system, there is a popular belief that learning and applying fuzzy system is much easy. We'll see that. Designing by experts, neural network designed by expert is almost impossible. Well, fuzzy systems, you can do it. Augmenting expert knowledge, I consider this a very important attribute when you are designing system from data. For neural network, it's not an easy job, but fuzzy systems, you have data, you extract the system, an expert looks at the system, and the expert finds that, okay, for this type of disease, there is an atypical case which was not present in the data, and it has not been modeled by the rule, so I add an extra rule, so you can augment it. Learning of the underlying principles, well, again, the popular belief is in 2 weeks you can learn fuzzy systems. We'll see how good it is. Unwanted generalization. Now here for neural network, unless one is very careful, it can really lead to very poor generalization even when the data is a little bit perturbed. I give an example. You don't need to work hard. Since it's a 3-class problem, one color corresponds to one class. I think I have 100 points from each class. You train a neural network, and this is the generalization produced by the network. Now here I have tried to use a very conservative approach. If the response of the correct class, response of one class is more than 0.8, and for all other classes less than 0.2, then I make a decision. Otherwise I say don't know. So this is the area where I don't make a decision. Nobody does that. Everybody takes the maximum value. Even if you do that, you see for this class, you find an area where you get a very high confidence for this particular class. Now, this is unlikely to happen with the fuzzy systems, you will see, because of the architecture of the system. It's easy to design a fuzzy system so that it can say don't know when it should, but for neural network, it's not an easy job. But there have been few attempts. We have also done something where you can make it to say so. So we see that there are some attributes which are good for fuzzy systems, but still, this is not the tool of choice. Why? I said that I asked these questions to many people. Some of the answers that I got is good and user-friendly toolboxes are not available for fuzzy systems. They are available for neural network. And usually people refer to MATLAB toolbox. And I must confess, I use MATLAB neural net toolbox if I want to check something quickly. But I never used fuzzy system toolbox. I tried to use a couple of years back, and I just hated it. So this is one of the reasons. Easy to generate useful solutions by ENN and with available toolboxes, but fuzzy systems it is difficult. If you try to use MATLAB toolbox, you will come to this conclusion that that is indeed true also. Will fuzzy modeling work for my problems? And this very sentence I have heard from a person who is a fuzzy expert, really. I mean, he does kind of fuzzy pattern recognition stuff, and he said, my problem is a forecasting problem, it's a little complicated, I need to do feature selection, will it work really? So, my impression and experience is designing useful fuzzy systems requires some engineering knowledge or engineering skill. I do not know what exactly I mean, but what I mean is really, you need to play with it long enough, you get a feel of what's going on probably. Otherwise it becomes difficult, but you can design very good system also. But if you see the website that I'm referring here, this is what you find. And this is a website created to hate fuzzy systems. It says that working pragmatic knowledge you can get in 1 week, and pragmatic knowledge of Mamdani method just 1 week. And you can be an expert in fuzzy systems. And I mean, this person does all kind of things. If you want, you can check this website. It's fun. So I'll just quickly go through 4 applications that I have my first-hand experience. And in all cases, neural network happens to be the tool of choice. One is structure-preserving dimensionality reduction, satellite image classification, which is a very important problem for countries like us, where we have natural disasters. We need to make quick assessment of that, the damage caused by this. Bounded weak ecoregion detection, this is related to severe weather prediction, and identification of biomarkers for cancers. The last one I'll go in little details in context of some unsolved problem. So structure preserving dimensionality reduction, what do I mean? This is really a work of Salmon, long back he did. You have a set of points in p dimension, it's high dimension, and you want to find out for every point a q dimensional representation so that quote unquote the structure, the interpoint distances are preserved. So what he did is he used an expression like this. You can easily ignore this part because this is constant for a given data set, doesn't have any role on the optimization. I kept it because Salmon kept it. So this is the distance in the original space, this is the distance in the reduced space, and this is kind of normalizing its component so that outlier doesn't have much impact. So you try to minimize this kind of objective function to learn this unknown set of vectors y. And typically gradient descent is used, and it works really, really good. Well, if it works good, what am I going to talk about today? We'll see it. So let's consider 3 simple data sets. I'll show some results. One is elongated clusters, which is like this in 3 dimensions, and an helix like this, and a sphere shell, which is difficult data for projection. You have a hemisphere, and then you have a thin shell. So if you make linear projection on any side, you will never be able to separate them. So we call it nonlinear data. Now the first data set, if you do the scatter plot of 2 components, this kind of picture you get. So this gives you a feel of the data. And this is the output you get from Salmon's algorithm using just gradient descent, so which is really, really good. For sphere shell, fantastic output, you get a very clear representation. And for helix also, you get a very good output. It works good, but there is some problem. It's a computational procedure. It doesn't have a prediction ability. So if you get one extra new point, you have to rerun the whole optimization process. There have been few attempts to make it simpler, but still you have to do the optimization process. So people have tried to use neural network and fuzzy systems so that you can predict for unknown data points. And here are some results. This is from neural network. This is from fuzzy systems Mamdani-Asilian model. You can see the smoothness is not very much there. TS model does a reasonably good job except this area. I deliberately show this poor result because other cases I'll show good results. If you use a higher order model, it does a better job too. And this is for the elongated data sets. Again, you see they are fairly nice by all systems. Sphere shell. Now here for neural network, this is one of the best output we could generate. So you can see the mixing up. And also look at the rectangular shape kind of. The Mamdani model looks little better. The TS model, that is much better. The overlap here is very minimal and you get really the spherical shape here. Satellite image classification. This is again, as I said, is a very important problem. I'll just refer to two data sets which have some interesting characteristics. These are all 7-channel Landsat image. This one corresponds to some area in Atlanta. This one corresponds to some area in Vienna. And there are 7 categories. And watch the distribution. In one group, you have 176,000. In one group, only 740. This is also kind of skewed, but still more balanced than this one. And this data set, these two data sets have been used by many people. This is the pictorial representation of the first image we call sat image 1, and this is the ground truth. Fortunately, we have ground truth for every pixel here. And this is the second one, and this is the ground truth. Now what we did here is, from first image, we took 200 randomly selected points from every class to design the training set. We generated 4 such training sets and tested on the whole image. Why did we take 200 points from each class? Because the literature has results with exactly this partition. And for the second one, we took 800 points from each class, but the literature has some results where the minimum number of points taken from one class is 922. So this is more conservative, using less number of points in the training set. If you see pictorially, this is the ground truth and this is the output produced by the system. Here also this is the ground truth and this is the output produced by the system. They're a fairly good match, and that will be clear from here. Like if you see the test error, these are the test errors for 4 realizations. And we'll see that even the worst error, which is 14.47%, this is about 7% better than the best results reported in the literature. And these are using simple fuzzy rules. Similarly, for the other system also, it doesn't do much better, very comparable to what is available in the literature, a little better. I want to draw your attention here on the number of rules that the system extracted. It has something to do with knowledge discovery, because after this data have been processed, people physically found that there are 12 subgroups in the data. And you see the number of rules is close to 12 or 11, 12, so very close to that. So you can, and the more we discuss, you will see that each rule corresponds to one type of area. So one can do knowledge discovery using this kind of system. So this I have already mentioned. So this simply says what others have found. Many people have tried to do it. And the fuzzy rule does much better than others. And you can improve the results much further using context-sensitive inferencing. That's also part of fuzzy systems. But I'm not going into details of that. The next problem is the bounded detection of bounded weak ecoregion. Now these are some signature in the radar images, small scale signature. If you can detect this quick enough, then you can predict severe weather phenomena like thunderstorm. You don't get much time, between the detection and the prediction time, like if you can detect now, probably the thunderstorm is going to appear in 2 hours or so. So this is a very important problem. I do not really understand the physics of the problem. I looked at completely pattern recognition point of view. I read some paper on this by a group in NOAA in US, and they tried to use all kind of tools. So we thought that fuzzy systems can do a reasonable job, so we did a collaboration. So, I'll talk about that. Just to give an idea what a BW, this is the horizontal cross section of a radar scan, and you have a BWR here, unless I point it out. There is some structure here, I don't know whether you can see it or not, but if I see more closely, I see similar structure at many other places also. But that's BW here, and one has to detect it, and you have these stacks of such images from there. So it's difficult because it's small scale feature, and the number of the major problems, the number of false alarms that you get, they're very high. And also these vertical aggregations become very difficult when the storm moves pretty fast. And so for there is several problems. So it's a difficult problem. I will probably skip about all this data generation, etc. Now they have used fuzzy systems and all other kinds of tools, genetic algorithms also, and we try to simple fuzzy rules for these systems, and it appears, at least for this data set, it works better than others, which appears in Journal of Applied Meteorology and Climatology. And the advantage is you can aggregate this stack of output using fuzzy rules which an expert can give to get a 3D representation of the system. So what do you find? The biomarkers I shall discuss in details in the context of some unsolved problems. So we have at least few problems where fuzzy rule-based system works great, but yet neural network and other tools are preferred. So what are the real difficulties? Let's see, if we try to solve this problem using neural networks, say multi-layer perceptron, they're all function approximation or classification type problem. What you need to choose? Number of nodes in the hidden layer. Activation function, typically you choose sigmoidal, so not really a choice. And then just train using backpropagation or Levenberg-Marquardt or some other learning algorithm. If you use radial basis function network, the picture remains the same. Suppose you want to solve the problem using fuzzy systems. You have to decide on the number of rules. You can think this is as good as number of hidden nodes. Probably not. Number of linguistic values for each input, which is number of fuzzy sets for each input. The shape of the input membership functions. You want to use triangular, trapezoidal, Gaussian. I don't consider this as a difficult one because all of them work equally good. Gaussian is a good choice, it's differentiable, easy to handle. Choice of T norms for computing the firing strength of a rule. Typically people use mean and product. Product has some counterintuitive implications, and mean has other problems like when you try to tune, it's not differentiable. So there are solutions to get around this problem. Still easy to decide on. If you use Mamdani type model, you have to decide on the number of linguistic values for the output variable. You have to also decide on the shape of the output membership functions. If you use TS model, then you have to decide on the choice of the consequent functions, like whether it's a linear function, quadratic function. Suppose, and there is an expert who can decide on all these things. Suppose there is an expert. Even then, you have issues like, I say use 10 rules. I say use Gaussian membership functions, but how do you initialize the system? For neural net applications, we all use random initializations, and we know that it works great, but fuzzy system doesn't work. It really doesn't work. So still you have problem how to initialize the system, which means you have to do some kind of exploratory data analysis. So it indeed demands much more from an expert if you really want to do it. And if you are a practitioner, you don't have time for playing with all these choices. Now, what are the solutions? Well, Sugano really again came forward in many occasions. He gave many interesting things. In 1993, he came forward and gave a really good solutions to attack almost all of the issues that I have mentioned. It's a classic paper and the first work of this kind, and so far the most complete work, I would also say. Now, the basic idea is a cluster can be translated into a rule. That's the basic idea. And it also helps because many people say fuzzy system has a problem of rule explosions. It also helps to avoid that because the number of clusters you find in the data is finite, so you have always limited number of rules, not explosion. To get an idea what you do when you try to find rules from data using clustering, let's consider an example, a two-class problem. We have to classify cow and dog, and life is very simple. So we have data like this is two-dimensional data. If you scatter plot, the cow data look like this, the dog data look like this. So very simple type, hypothetical example. And this is the centroid of this data, this block. This is the centroid of this block, this is the centroid of this block, this is the centroid of this block. And what I am doing is now, so around the centroid, I put a hat like this, a Gaussian hat. And I am modeling something I'll call the input is close to this vector V1. So I say if input is close to this vector V1, then it is a cow. If it is close to this vector V4, it's a cow. If it is close to the vector V2, it's a dog. If it is close to the vector V3, it's a dog. And we have 4 clusters and I have 4 rules. And you can easily see that this is going to work, right? So 4 clusters, 4 rules, and here are the 4 rules. X is the input, which is a two-dimensional vector. If it is close to V1, it's a cow, so you have already seen. Okay, it looks very simple. So if we can find the cluster, we can find the rules. What about this? Suppose these data come for the cow and these are for the dog. Question is, if I ask you how many clusters are there, I think the natural answer is there are 2 clusters. But you can easily see if I try to write something, the centroid for this might be here. I can make it more funny so that the centroids fall somewhere here. And then if you try to use this kind of rule, it's not going to work. How many clusters? Answer is definitely 2. But it's not good for our job. Will cluster validity help? Because cluster validity, many researchers have used in this area to decide on the number of rules. But it's really not a good idea. It cannot solve because cluster validity deals with clusters in the pattern recognition sense. So will clustering work here then? The answer is surely yes. If we do something like this, instead of finding 2 clusters, if we find 8 clusters or 9 clusters, and for each of them, if I write a rule, it's going to work, right? Okay, so this is a really cool idea of using exploratory data analysis for clustering, but it invites more problems too. How many clusters to look for? So this is related to really the number of rules. Which clustering algorithms to use? There are plenty available. Is the existence of cluster structure necessary in the data to apply clustering? We have seen a case where the natural cluster does not correspond to the rule, but still we can work with it. But if the data do not have cluster, can we really use it? For non-classified data, we have input as well as output. So where should we cluster? In the input domain, projected on the output, in the output domain, projected on the input, taking input output together, separately. Then how to translate each cluster into a rule? So there are more problems now than we had earlier. Well, what Sugeno did, I must mention here because that's still the best work. He clustered the output data and projected the cluster structure on the input. He used the fuzzy C-means clustering algorithm and decided on the number of rules or the number of clusters using a cluster validity index. But again, this index is good for pattern recognition type of problem, not for rule extraction. Well, it did work for some of the data that he has used, but this is not good for, I can easily give you a data where this is not going to work. Just think of a data, it's just on straight line. The function is a linear function. You try any cluster validity index, you will have trouble. There's no cluster in the data. He projected the output clusters into the input, as I mentioned already. And he also used this, the membership functions that you get from the fuzzy clustering algorithm to design, using least square method, trapezoidal membership functions for the fuzzy rules. For structure identification, now this is something very important I want to emphasize, and this is an open problem still, which really refers to how many inputs should you use. Find out the inputs which are important. He used some criteria functions, and in an iterative manner, find the best feature, then augment it with another one. But you do not, it doesn't give you the guarantee, it doesn't give you guarantee to get the best structure that you have. It's an incremental method. As I mentioned, still after that there have been an explosion of work in this area. Many people have tried to do these things, but still that remains the most complete one. I went in the wrong direction probably, yes. So what are the problems? Structure identification, still an open problem. So in a fuzzy system, how many inputs should you use? There is no good solutions yet available. I will spend some time and try to give some solution to this. How many clusters to look for? All the work that I know, there people have tried to use usual cluster validating index, but that's really not a good idea. It's conceptually not acceptable. Still, it's an open problem. How to deal with really very high dimensional data? No solution exists. There are few attempts where people have tried to design a hierarchical system that is combined variable, but once you combine variable, the interpretability of the original system is lost, and then the attraction of fuzzy system is lost. And moreover, if it's really high dimensional like 1000, it's not going to do the job. I will discuss in detail some method which will take into account both 1 and 3 together. Which clustering algorithm to use? In fact, here it's not an issue. Any clustering algorithm will do equally good a job if you can choose the right number of clusters. But if you want to use the membership function, then you should use fuzzy clustering algorithm. And if you use something like possibilistic fuzzy Siemens algorithm, it's better for rule extraction in the sense the centroids are less influenced by the outlier, so therefore the rules you get, they are better. For non-classifier applications, that is where both you have input and output variables, the most natural choice in my view is you augment input and output, because that's where you want to find out compact areas. So you input augmented by output, that's the most natural choice. If you do, you can also separately cluster an input and output, but then you have to establish a correspondence between the two. But still you can do a reasonably good job, but the main issue still will remain how many clusters to look for. Choice of membership functions, well, triangular, trapezoidal, Gaussian, all are equally good, but I prefer the Gaussian one because you can easily get a crude estimate of the spread of the membership functions from the data falling into the associated cluster. It's differentiable, and also it's extended to infinity, so this gives you some advantage. You never get the rule base incomplete, but actually I do not consider it an advantage, it's a disadvantage in some sense, because if you want to make the system say don't know when it should, triangular trapezoidal memberships are better. The seventh is related to the first one. Fuzzy rules when you extract from data could be incomplete, which means you get some data and the no rule is fired. Neural network, this is not going to happen. You will get some output. Question is it good or bad? It's really something of advantage, because this is a situation you don't want to make a decision. Because this is an example where you had no representation in the training set. Rule simplification. This is a problem, it's not well attended in the literature, where the whole idea is when you design the system from data, you get many membership functions which are almost the same. So there are several attempts to simplify rules, but still no well accepted. So there's still a lot of scope to do work in this area.